Ever wondered why you land in the same spot when you jump inside a moving train? But if you were to jump on its roof, you'd land in a different spot? This, my friends, is a fascinating paradox that combines the thrill of a leap with the intellectual rigor of physics. It's a classic puzzle that's been puzzling minds for ages, and it all boils down to two fundamental concepts: inertia and the principle of relative velocity. Inertia, the property of an object to resist changes in its state of motion, and the principle of relative velocity, which tells us about how the speed of an object varies depending on the observer's motion, are the two key players in this intriguing scenario. Together, they weave a fascinating tale of motion and forces, a tale that will take us inside a moving train and then quite literally on top of it. So let's dive deeper and understand this intriguing phenomenon. To get to the bottom of this first, we need to understand two key concepts: inertia and relative velocity. Inertia, in simplest terms, is the property of an object to resist changes in its state of motion. It's the reason why you lurch forward in a car when the driver hits the brakes suddenly. The car stops, but your body, due to inertia, wants to continue moving at the original speed, hence you lurch forward. Now imagine an ice hockey puck sliding on a smooth, frictionless ice surface. Once it's set in motion, it will keep sliding in a straight line indefinitely. This is because there are no external forces acting upon it, and due to its inertia, it maintains its state of motion. Next, let's unravel relative velocity. This is the velocity of an object as observed from another moving object. For instance, think about two cars moving parallel to each other on a highway. If both are moving at the same speed, a person in one car will observe the other car as stationary, even though both cars are moving. This is because the velocity of the second car relative to the first is zero. Now let's consider a different scenario. If the first car speeds up, the person in it will observe the second car moving backwards, even though it's still moving forward. This happens because the velocity of the second car relative to the faster first car is negative. In reality, the speed and direction of both cars haven't changed. What has changed is their velocities relative to each other. This is the essence of relative velocity. To sum up, inertia is the property of an object to resist changes in its motion, while relative velocity is the velocity of an object as observed from another moving object. Now that we understand these concepts, let's apply them to our train scenario. Imagine jumping inside a moving train. What happens? You might think you'd be flung backwards, but in reality, you land in the same spot. This is due to a principle known as inertia. You're not just jumping up, you're also moving forward at the same speed as the train. So even while in midair, you retain that forward momentum. This phenomenon is also influenced by relative velocity. From your perspective, you're not moving forward or backward, you're simply moving up and then down again. To put it in simpler terms, you and the train are part of the same system. You're both moving in unison. You share the train's velocity, so when you jump, you're still moving forward with the train. This might seem counterintuitive, but it's one of the fascinating aspects of physics that govern our everyday lives, often without us realizing it. But what if you jumped on the train's roof? That's where things get interesting. Now, imagine jumping on a train's roof. The result is quite different, isn't it? Here, the jumper is exposed to an open environment where additional forces like air resistance come into play. This is unlike the situation inside the train, where the jumper, the air, and the train all share the same velocity. Outside, the air is stationary relative to the moving train. When you leap upwards, you still carry the train's forward velocity due to inertia. But now, you're battling air resistance, an external force that acts contrary to your motion. This force can slow you down, while the train continues to move forward at the same speed. As a result, when you land, you find yourself in a different spot on the train's roof than where you started. It's a fascinating demonstration of how varying conditions can change the outcome of the same action. So there you have it, the same action, two different outcomes, all thanks to the fascinating laws of physics.